Hey, hi there. In the previous video, we learned how to perform t-test. We understood the t-distribution. We also saw how we calculate the t-critical value from the table. We also got to know that in Python, we have simple functions which we can easily use without the need to refer to a table to calculate the critical value. So today we'll be discussing chi-square test. Now, what is chi-square test? Just like we had a t-distribution, right? When doing a t-test, we also have a chi-square distribution when we do chi-square test. So it assumes that the data points belong to a distribution which is called a chi-square test, chi-square distribution. So this distribution basically is used in the common chi-square test for goodness of fit, right? So chi-square test can be used to find the goodness of fit to evaluate whether a particular data point belongs to a distribution or not. Okay. Then the independence of two criteria can also be evaluated using chi-square test. This is something which we are going to do in our Python notebooks as well, where we have two categorical columns and we want to evaluate the dependency of each other, right? That is when we use chi-square test. So if you notice the t-test, the z-test, typically these are hypothesis tests which are done on continuous distributions, right? Whereas chi-square test can be done on the categorical data as well. So in confidence estimation so chi-square test is also used in the confidence interval estimation, right? For normal distribution. So there are many uses of chi-square tests. But rather than looking at the theory, let's first try to understand what its application. Okay. And if you understand the application, all these 3 points can be easily understood. So if you look at chi-square test, this is how the distribution looks like. And just like we had a t-distribution, we had a number of data points. We saw for t-test, t-distribution, as the number of data points increased, it approached towards a standard normal distribution. So here also degree of freedom, number of data points, degree of freedom is just number of data points minus 1. So both of them represent number of entities, right? So as you see, the degree of freedom increases, right? Correct. My graph becomes more and more, skewed towards my graph becomes more and more towards a normal distribution or a bell curve, right? I would say. So this is for the blue one, DF1. And slowly, if you keep on increasing the number of data points, right, it approaches a bell curve. If I have DF30 here, so this will be more something like this. For DF30, this will look like this. The curve will look like this. So this is something which we noticed with Poisson and binomial distribution also. When we increase the number of trials, then all these distributions tend towards a normal bell curve or normal distribution. So if you look at the distribution now, you can see here that, for less number of data points, like say for DF, less than 30 or 40 or whatever it is, the distribution is not symmetrical, right? It may not be symmetrical, unlike t-test and z-test, t-distribution and z-distribution, right? So when you do two-tailed test, just like we did it in the t-distribution, we attach alpha by 2 on each side. So here, on the right-hand side, the skewness is high. So the alpha by 2 value is, approaching more towards the left-hand side. Whereas on the left-hand side here, the area covered, it is less skewed. So the area is covered with less amount of shift from left to right. So this distance which you see will not be same, of course, because it is not symmetrical. But this area will also be alpha 2. This area will also be alpha 2. One on the left-hand side, the area is somewhat taller. On the right-hand side, it is more flattered. So the distance covered here is more to reach alpha by 2 value for two-tailed test. And one more thing you have to notice is that your data point starts from 0. The chi-square values start from 0. So it is meant for a positive distribution of data. Okay, unlike the z-test or the t-test, which can handle negative and positive values, but this is meant for positive values only. So now let us understand how we do the chi-square test. So chi-square test typically are of two types. Okay, one is called as chi-square test of variance. Okay, so chi-square test of variance, here we basically compare the population variance with the hypothesized variance. So basically we have a sample variance and we try to compare it with the population variance. Okay. We can hypothesize variance means we can call it a sample variance as well. So the formula is like this. This is a chi-square. It's a Greek letter chi-square notation. This is equal to n minus 1. N minus 1 is nothing but degree of freedom, right? Into sample variance divided by population variance. S square is sample variance. Sigma square is population variance, right? Correct. So if I have a one-tailed test will look like this and a two-tailed test will look like this. If this is 5%, this will be alpha by 2 on each side. This is say 5%. This will be alpha by 2 and this also will be alpha by 2. 2.5%, 2.5%. Okay. Now let us take an example of chi-square test of variance. Okay. The following is the income data of blue collar workers who are at the same skill level. There are two groups of workers of the textile company Lorries and Co. and workers of the general population. We want to check whether the variance in the income of Lorries is higher than that of the general population. So Lorries and Co. is basically a company and they have workers in them and there are different level of different workers like blue collar, white collar, whatever it is. So they are trying to see whether there is a variation in these blue collar workers. And if this variance or if this variation is much higher or significantly different or higher than the general population, right? So basically they're trying to see the difference in the, pay grades of blue collar workers for Lorry and Co. So let's just look at the data points. These are data points given. Mean and variance of the general population is given to you. Now, this typically comes from, historical data. Okay. And this is what the sample data is, Lorries and Co. So from Lorries and Co, I can easily calculate the samples variance and the number of data points on the degree of freedom or number of data points, right? So what are the null and alternative? So these are the questions. What are the null and alternative hypotheses? Is it a right tail or left tail test? One sample or two sample test? Is it a test of mean, proportion, or variance? Which statistical test do you think is appropriate? All these questions we have already done for t-test, I believe. So what are null and alternative hypotheses? So please understand, guys, the difficult part always forms the alternate hypothesis. Do not forget that. So here, let's say, what is the question being asked? Whether the variance in the income of Lorries is higher than that of population. That will be my alternate hypothesis. Now it is saying higher than. It is not saying not equal to, right? Or it's not saying is not significantly different. Right? If it would have asked significantly different, then I would have gone for higher than and lower than also. But specifically asking for higher than, which is one tail test, which means it's a one tail test. So what I'll do, so basically I'll say variance, say, or sigma square, whatever you want to write. Variance in Lorry is greater than variance in general population. And H naught will be less than equal to. Very simple. So let's see. See, here, V1 is equal to VP, variance in income is same as the population, less than equal to or equal to, it's the same thing. And then this will be V1 greater than VP, variance in income of Lorries is higher than the population. So sometimes looking at the question, we might have to come up with the alternative hypothesis first, and then go with the, null hypothesis. So this we can write as less than equal, it won't be wrong. I put it equal to, because they are asking for if it is greater than, right? So equal to also makes sense, less than equal also makes, doesn't matter. Ultimately, we'll be evaluating this. Okay. So what are null hypothesis, alternate hypothesis? This we have already evaluated. Is it a right-tailed or a left-tailed test? Now, since we're talking about greater than sign, it will always be a right-tailed test. Always remember that. Two-tailed to hai nahi. It's a right-tailed because it is greater than, right? Okay. Right-tailed test. So next, is it a one sample or a two sample test? This is a one sample test. Why? Because we're talking about one sample. The other sample is the population. We're comparing with the population. One sample test. Is it a test of mean, proportion, or variance? It's a test of variance. We can do t-test and z-test for proportion also. Okay, but doesn't matter. We can. So there are a lot of other tests, theoretical tests, which are available, but I'm covering the ones which are most relevant in today's world. Okay. Which statistical test do you think is appropriate? Of course, the chi-square test of variance. Okay, chi-square test of variance. Now let's see how we build the solution, how we do the calculations. So step one, we assume alpha to be 0.05, 5%. Degree of freedom is found out to be 14. It is equal to n minus 1. Number of data points here is 15. Minus 1 is 14. It's a one-tailed test. And given these three information, we refer to the chi-square table. Okay, just like we referred to the t-test, t-table, right? So one from the chi-square table, we'll calculate the chi-square critical value, which is 20.68. And I'll show it to you in the next slide, how we refer to the table. Same way that we did it for t-test. So next, step 2, with the parameters given to us, population mean, sample standard deviation, population standard deviation, will calculate the chi-square statistic, which is 35.62 using this formula of chi-square test of variance. I've written population mean as MP. You can write this mu, not a problem. This also you can make it sigma. Okay. Step 3, finally, we got to know that my chi-square statistic is greater than my chi-square critical. This is 35.6, this is 20.68. That's why whenever the statistics is greater than the critical value, doesn't matter what test we are using, my H0 will always be rejected. If my test statistic is greater than my critical value, my H0 is rejected, which means what? My alternative hypothesis is accepted, which means that the variation in low-risk company is indeed higher than the population. Right? So the variation is significantly higher than the population variance. My alternative hypothesis is accepted. My null hypothesis is rejected. Now let us try to visualize this so that we can understand in a much more clearer way. But before we do that, let's quickly check the calculation of chi-square critical value from the chi-square table. Very simple. So here, what are the data points which we have? So what is the information given to us? Alpha is equal to 0.05, one-tailed test. Degree of freedom is 14. And if you look at the table now, right, alpha 0.05 will be that column. Degree of 14 will be this row. And finally, I have the intersection at 20.685. So my chi-square critical value is 20.68. So the intersecting point lies at 23.685, which means my chi-square critical value is 20.68. This is how we calculate the same way which we did it for t-test. Right. All right. So now let's try to visualize and understand much more clearer way. So it's a one-tailed test. We all know that chi-square critical is 20.68, alpha is 0.05. So this region on the right-hand side, which you see, is alpha is equal to 0.05. And my value here is 23.68, one-tailed test. Chi-square is on a higher side, of course, right on the right-hand side, because my minimum value, which is chi-square distribution can take, is 0. Right? Okay. So once this is done, next, let's look at the chi-square statistic value. Chi-square statistic value is 35.62. So it will cross this value of chi-square critical, right? And this area on the extreme right-hand side will be my p-value. So my p-value is less than alpha, which means that is lying in the rejection region. Hence, my H0 is rejected. So chi-square test can be used for finding out the dependence between two attributes as well. In the previous example, we saw a typical application of chi-square test of variance. Now we'll also try to see how you can use chi-square test to determine the dependence between two attributes. And this test is called chi-square test of dependence. All the process of calculating the chi-square critical, comparing with the chi-square statistic will remain same. The graph everything will remain same. Just that the formula to calculate the chi-square statistic will change. Okay, because that is chi-square test of variance. This is chi-square test of dependence. But let's try to see the example first and try to understand what scenario we can use chi-square test of dependence. Die is thrown 132 times with the following results. Okay, number turned up is this, frequency is this. Okay, so basically we're throwing a die 132 times. Okay, number of trials is 132, and the number turned up are these 6 sample space, right? The possible outcomes 1, 2, 3, 4, 5, 6, out of which 1 came up 15 times, 2 came up 20 times, 3 came up 25 times, 4 came up 14 times, 5 came up 29 times, and 6 came up 28 times. So these are my observed frequencies, guys. These are my observed frequencies. So in chi-square test of dependence, we deal with frequency calculations. Just like in chi-square test of variance, we calculate the variance, we compare the variance. Here we'll be comparing frequencies. So what is the question being asked? Is the die unbiased or not? Is the die unbiased or not? So the first step would be, so this is the table given to me. Let's look at the solution now. These are my observed frequencies, as I told you. Now, what will be the formula which I'll be using? As I told you, the formula will be slightly different from that one, which we were using for chi-square test of variance. So here it is summation of O minus E whole square divided by E. O means observed frequencies, E means expected frequencies. Summation why? Because there are different data points, different labels or categories. We add them to get the chi-square statistic value. But before we go there, what is the null hypothesis and what is the alternate hypothesis? As I told you, the difficult scenario is always placed in the alternate hypothesis. And that's why my alternative hypothesis will stay, my die is biased. And my null hypothesis will be die is unbiased. Okay. All right. So next we calculate the expected frequencies. Now here the expected frequency luckily is an easy calculation. Why? Because we know that my expected frequency will be number of times, the number of trials into probability, right? Correct? Because for every data point which is here, right, what will be my expected frequency? It will be n into p, because 1 is basically the probability of 1 occurring for one trial is 1 by 6. And if I have 132 times, because the probability of me getting 1, if I throw the die 1 time, is 1 by 6. And for the other numbers as well, if you throw the die only once. And since I'm throwing the die 132 times, this probability of occurrence will get multiplied by 132. And that is my expected frequency. What should have happened? And this is what actually happened. During the probability calculation step, I told you, right? When you calculate probability, these are chances, likelihoods, right? Not the actual outcome. If you throw a coin 2 times, you may get 2 times head directly. But if I ask you what's the probability, you always have to say both heads occurring at the same, occurring from both coins, 1 by 4, 25% probability. Right? So similarly, we are saying that 22 should be the expected frequency for all of these numbers, because the probability for each of their occurrences is same for one trial, which is 1 by 6. Okay. And then I have to calculate the O minus E divided whole square divided by E. That is what we have to do here. Okay. And then chi-square, which means that chi-square is equal to 9.59. I have to add all these values, so I'll get chi-square statistic. Actually, it should be chi-square statistic equal to 9.59. Now, chi-square statistic is 9.59. My degree of freedom, there are 6 data points here actually, sample outcomes. 6 minus 1 is equal to 5. My alpha is equal to 5%, right? Which I typically assume. Given this information, right? And this is one-sided test only. So chi-square will be 11.03 from the table. You can check. You can go back and check from the table. My chi-square critical value will be 11.03. We don't need to look into any tables when we are in the corporate, because we have inbuilt functions of Python which you can typically use to calculate the chi-square critical value as well as the chi-square statistic value and the p-value as well. Okay. Now here, chi-square statistic is actually less than chi-square critical value. So if it is less than that, null hypothesis is accepted. Very soon. And you can easily visualize this also. Right. I leave that to you, the homework. And this is how we use the chi-square test to find dependence as well. There is, so here the chi-square, so here the expected frequency calculation was very easy, right? For all these different labels or categories. But when it comes to handling real data, right, there may be n number of categories. And there, the expected frequency may not be as simple as this calculation. So what do we do there? We feed in the observed frequencies, right, into a function from scipy.stats, which is called as chi-square test. And there it calculates the expected frequencies and also gives you back the p-value and the chi-square statistic value. Okay. So now let's see how to calculate the p-value and the chi-square critical in Python. So if you look at, so basically it takes one single line of code to calculate the p-value and chi-square statistic. So once we have the p-value, then we can compare it with the alpha value, right? So how do we do it? First, so how do we do it? We use a function for chi-square statistic. We use a function which is called as stats.chi2_contingency. And this function requires only one parameter. And the parameter is the observed frequencies, the matrix of the observed frequencies. Okay. In the previous question, the frequencies were given to us already. So it was a theoretical question. But in the real world, whenever data set, the frequencies will not be given to you. We have to calculate the marginal frequencies using pandas.crosstab. Suppose I will give an example. If I have one column which says employee attrition, 101010. 1 means person has left the company, 0 means the person is still there in the company. And there is one more column called, let's say, travel. It basically talks about the employee, whether he travels frequently, travels rarely, or there is no travel involved in his job. And the data which we have is at the employee level. Like each row has information regarding one employee. Now, if I want to see the impact of traveling on employee attrition, is it that a person who is traveling very frequently is more prone towards leaving the organization? If I want to check the impact, I'll use a chi-square test. And I'll use this particular function. But to directly use it, I need a contingency table for that. Contingency table is something which we had already discussed in while studying marginal probabilities. Same way we'll do pandas or crosstab. What crosstab? What it will do? It will segregate out all the labels for us, right? And it will create a matrix of all these possibilities, conditions. Travel frequently for 0, travel rarely for 0, and T for 0, and similarly for 1 as well. Right? So it will be a 2x3 or 3x2 matrix. And I'll put that matrix inside this function. So this function not only calculates the chi-square statistics and p-value, but it also calculates the degree of freedom and the expected frequencies as well. Okay. Right. And the p-value which we'll get will be for a two-tailed test. If you want to do it for a one-tailed test, we have to divide that p-value by 2 and then compare with the alpha value. Okay. I can also find that the chi-square critical. Okay. Once we find the chi-square critical from Python, I can compare it to chi-square statistic. How do I do it? I use this function stats.chi2.ppf. It requires 2 parameters, 1 minus alpha, the degree of confidence, and comma, the degree of freedom, the confidence and the degree of freedom. Right. However, for two-tailed test, I have to do 1 minus alpha by 2. Okay, this is done to calculate the chi-square critical value. But if I want to compare with the chi-square statistic, again, I have to use this formula because I need the chi-square statistics value, right? So it's better to use this process, one single step, right? Either way you can do it, but both of them will give you the same result. Okay, so that's it for today, guys. I hope you enjoyed today's video. I hope you're learning a lot, and we'll do all of these. We'll apply all of these theoretical concepts in Python as well. So please check out those videos as well. Go through them and please practice more and more. We'll also provide you some case studies to work on. which will drive your hands-on experience and help you solve real-world problems. Okay. So guys, wish you all the best. Take care. See you in the next video.